All right, this video is to show you how to do the graphing for your Dune Buggy lab. So here's what you're going to need. 2 small pieces of graph paper. You are going to need a calculator, glue, 4 different colors, and your ruler or a straight edge. Before we do anything on the graph paper, we're going to attach it to our journal page. So on page 7, take your 2 pieces of graph paper and just set them down so that they are not overlapping, so you've got a space in between them. And then you're going to take this left edge that's right next to the inner binding of your notebook, and you're going to just fold that edge in. Doesn't have to be perfect. You can do that on both pieces. And then take your glue, put a nice thin line of glue right along that tab that you just made. Flip it open so that it's attached to your journal page. And again, do the same thing down here. I'm going to flip it open and attach it down like that. So now we have our 2 graphs ready to be marked on. We're only going to focus on just this top graph paper today. Everything we do in this video is going to go on this top graph. We're going to leave the bottom one completely blank for the time being. So the next thing I want you to do is take your 4 colors, and you're going to choose one color to represent each of your 4 Dune Buggy runs. So mark on your paper somehow which color is going to represent which run. I'm just going to mark around my headers. You can shade it in if you're using pencils. You can just put a dot, whatever you want to do, so that you know this color is representing this data set. And there we go. So I've got my 4 colors marked over here. Now, when we look at our information today, we're looking only at the time in ticks and our total distance in centimeters. We're going to completely ignore that middle delta D column. The first thing that we're going to do on our graph is to draw in our X and Y axes. And we're going to do that a little bit differently on this paper. So I want you to look at your graph paper, and I want you to come all the way out to the right edge and find the last blue line along that right edge. Go about 1 or maybe 2 lines up from the bottom and mark that last line just right on the edge of the paper, and we're going to label that 10. Even if you didn't have 10 ticks in each of your runs, we're going to go ahead and label it 10 so that everybody's graph is the same. Now go over 2 lines from there and mark that 9. So see how I've skipped a blue line in between. Do that again and keep doing that, counting backwards. 5, 4, 3, 2, 1, and my 0 is right here. It's right up along the far edge, and that's okay. We may have to write on the actual notebook paper a little bit to label our axes, but that's all right. That's why we have it attached beforehand. So the next thing you're going to do, take your ruler or your straight edge and go on and draw in your x-axis. Just trace right along that line. And you're going to label it time, and always put your units. In this case, our unit of time is going to be ticks. And that's because if you recall, we weren't counting seconds or half seconds or anything like that. We were just keeping a steady beat. Tick, 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 tick. So that's why we're using that for our time. Now right here where you drew in the 0, right along that line, go on and add your y-axis right there. And your y-axis is going to be total distance in centimeters. Always label your axes. Now we're going to scale our y-axis just exactly like we did in the tile lab. So the first thing I need to do is count how many lines I have available on my y-axis. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have 12 lines available on my y-axis. The next thing I need to do is to look at my total distance column for all 4 runs. And I need to find the very highest number out of all 4 of these columns. And in this case, my highest number is 338 centimeters. Yours may be different, but find your very highest number out of the entire page and circle it. That's what you're working with. Now you're going to take this number, the highest total distance, divided by how many lines you have available. So in my case, that's 338 divided by 12, and I get 28.1666666. We're going to round up to the nearest whole number, or in this case, I'm actually going to round up to the nearest multiple of 5. So instead of rounding that up to 29 and trying to count by 29s, I'm going to just round that up to 30 and count by 30s. So each line on my y-axis is going to represent 30 centimeters. So count by 30s. 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330, 360. So I'll have a little bit of space on top of the graph, and that's okay. And if you look a little bit closer, you can see that I've written actually off of my graph paper a little bit and onto the journal page beneath. And again, that's okay. That's why we have it attached beforehand. So the next thing that we're going to do is to actually graph our data. Pick a data chart. It doesn't matter which one. Take the color that you have marked to represent it, and we're going to graph all of those points. So my first one is at 39. Second one is at 79. Third one at 112.5. Fourth one at 146.5. Then 176.5. Then 208. Then 240 exactly. Then 270.5. Then 306.5. And then 338. So I have this nice, beautiful stretch of dots here. In the same color, I'm going to take my ruler and I'm going to draw a line starting at the origin and ending exactly at that last dot. So line up your ruler, start at the origin, finish it right on your last dot, and go on and draw in a line. The next thing you're going to do with that line is to find the slope of that line. And this one is really, really easy. All you have to do is take this last data point, which in my case is 10 ticks, and 338 centimeters. Okay, my X value is 10 ticks. My Y value is 338 centimeters. And remember that slope is equal to our change in Y over our change in X. In other words, change in total distance divided by our change in time. And since our line is starting at 0, 0, we can just use these values. In this case, it's going to be 338 centimeters divided by 10 ticks. Never ever leave your slope like this. If you need to plug that into a calculator, do it. Hopefully you don't need to divide by 10. When I do this, I get 33.8, and in this case, centimeters per tick for my slope. So now I'm done with this green one for now. You're going to do the same thing for the rest of your 3 data charts to get 4 different colored lines on this graph. Every time you draw a line, find the slope of that line, and then go on to your next data chart. Now notice on my purple line here, I only go up to 8 ticks because my data stops at 8. So when I find my slope, I'm taking my final point, 324 centimeters, and I'm dividing that one by 8 ticks. So don't always just divide it by 10. Take your last distance value, divide it by how many ticks you're at that point. So in this case, 324 centimeters divided by 8 ticks. So I get 40.5. And there we have it. So when you're finished with your graphing on this top graph, you should have 4 different colored lines that correspond with your 4 different data sets. You should have 4 different slopes written directly on your graph in the 4 different colors that correspond to your data charts. So one more thing we're going to do on this graph. Take it and flip it open so that you're writing in the space underneath the graph. And we're going to write, this is a distance time graph. The slope of a line on this graph represents velocity, or distance divided by time. So what we've just created is called a distance time or a position time graph, and the slope represents the velocity. So now let's go back to those questions. So now let's look at our slopes. What does it mean in this case when the slope of our line is steeper? Well, the steepest one is the purple, and we can see that that's also the highest value. So on a distance time graph, a steeper slope, meaning angled more up, would mean a faster velocity or a higher velocity. When the slope is shallower, okay, like this orange one, that's going to be a lower velocity or slower. So what do you think it would mean if we had a zero slope? Zero slope would be straight across the graph, just like this. What would that mean about our dune buggy's motion? Think on that.